in this kind of in this webinar. I mean, I've been working for Northgate for about only about a year and a half. So housing is fairly new to me, relatively new compared to what I've done in my career. I've spent most of my time looking at clinical databases, very large clinical databases, and building reporting systems. But as I say, enough of me. Let's move on to the first slide. So the first slide there. So what we're looking at there, picture of sort of very crowded sort of slums in London. And sort of breeding grounds for cholera and typhoid. And I thought in these kind of COVID times, I thought this would be very topical. And I kind of thought to start the introduction to the presentation with a bit of kind of historical context and introduce a kind of, well, the work of this physician called John Snow, who was around in the sort of mid 1800s. And he was particularly interested in the prevalence of cholera and typhoid at the time. And the relevance of this is that the principles of which John Snow applied in determining the outbreaks of cholera isn't that dissimilar to what we're doing in predictive analytics and in data science in general. I wouldn't say that he was probably the founder of data science by no means, but I just thought this was in these COVID times, this is an interesting illustration of the application of methodology. He used principles of clustering and anomaly detection and all sorts of sophisticated tools to kind of work out what was going on with cholera. Now, the background here is that he spotted that there were particular outbreaks of cholera in London, in particular clusters. And I think that was curious at the time, because why was it in clusters? And the general theory at the time was that cholera was caused by bad particles in the air, or sometimes called miasma. And that was that was the theory, but he thought, well, that can't be right, because there were clusters of these outbreaks of cholera. And so what he did, he kind of meticulously went round knocking on doors and recording incidences of cholera from property to property. And then from doing all that meticulous work, he was able to map. And then creating these maps, and this map here on the right-hand side there, this isn't actually one of his maps. This is kind of an interpretation. What he did, he just drew little lines on next to the properties. But the size of the bubble there is proportional to the number of incidences of cholera, and he was mapping this. And again, the principles of that remain the same principles we use today, really, broadly speaking. And what he found was that these particular clusters of cholera were located around water pumps, and one water pump in particular. And through a kind of a method of elimination, he was able to work out this one particular water pump was causing, he thought was related to these outbreaks of cholera. And applying the principles of the scientific method, cause and effect, he thought, well, what would happen if I removed the water pump handle from the water pump? And lo and behold, the incidences of cholera suddenly plummeted. And then that changed. It was almost like a revolution in thinking. He was applying the scientific method. He was applying the principles of data science, kind of a bit of predictive risk. And I'll come back to this slide at the very end. But really, by removing that kind of water pump handle and then thus reducing the incidence of cholera, he found the connection. Obviously, it wasn't the water pump handle. What was happening was the water was being drawn from almost like the sewage system. So cholera is sort of bacterial. It was coming from the infected water. People were drinking from that water pump, and it was causing cholera. And he was able to go to another water pump that wasn't linked to the sewage system, and the people around that area didn't have the higher rate of incidence of cholera that this infected water pump actually had. So I just thought that was kind of just a gentle introduction, bit of historical context there about sort of an early example of the kind of looking at cause and effect and mapping, and looking at kind of anomaly detection. And I think I recall there was another instance where there was a couple of properties up here, and you can see my mouse moving over the screen there, where there was a small outbreak there, which is kind of a bit of an anomaly. That was almost like an anomaly detection. Why is there a small outbreak here? And I think further investigation turned out that particular person or household was actually having water delivered from that infected water pump. So that further kind of reinforced the view that it was actually the water that was causing the infection, not actually the miasma or bad particles in the air. But yeah, and I think that this quote here, you know, perfectly sums it up really. You know, it's about, you know, data science, predictive risk, you know, is finding patterns in the chaos of data and actually turning those patterns into kind of actionable insights. And hopefully, you know, a couple of slides later on, we're actually going to show you some kind of those kind of actionable insights. And some of the work that we've done here at Northgate is kind of like a proof of concept. So I'll come to that in just a minute, kind of conscious of time. We've got quite a few slides to get through, but yeah, anyway, so moving on, the ever expanding universe of data science. And I think the purpose of this slide really was to kind of distinguish between data science and business intelligence. Very often people, you know, sort of lump them into the same group, but there is a kind of distinction between the two. And at the bottom axis there, you know, you're looking at data, and you're looking at data in the past, retrospective data, and you got, you know, you're looking at data in the future. You've got looking into this kind of predictive kind of world here. And then on the y-axis, we've got very little you know, explanatory kind of purpose of the data. And as you go up this y-axis, you get more exploratory. It becomes more complex the further you expand out here. So business intelligence is something that I've worked in for a number of years, and I'm probably showing my age a bit, with clinical health data sets. And very typically, they were the KPIs, you know, what happened in the past. And you're kind of reporting in terms of, you know, key performance indicators, etc. But that in itself doesn't have much you know, it doesn't explore the data, it doesn't, you know, predict the data. And as we've moved in the last 10 years, there's been this kind of revolution, I think, that data science, you know, in a lot of jobs now, you know, a lot of data scientists being employed, whereas 10 years ago, there probably weren't as many data scientists. You know, we're catching up with the technology and so forth. But so you know, predictive risk kind of falls within this category. All this technique up here, we've got predictive modeling, we've got forecasting, statistical analysis, and we've got things like structured data, like ordered data, and unstructured data, like Twitter feeds, for example. And I think, you know, when I found this visualization, you know, that amongst the hundreds of visualizations out there, this really did capture my eye, but I think there was something missing. I think that there is another blob up here, which is prescriptive analytics, which is a bit more kind of like telling the end user, if you engage in, you know, this behavior X and Y, this is your expectation. So it's more prescriptive in its in its approach, but that's probably another topic for probably an entire topic for another conference, probably. But yes, I'd say prescriptive analytics would actually be here. But really, just the purpose of that is to show you where predictive analytics fits here, and it fits within the world, this kind of broad world of data science. So next slide. Some of you probably familiar Gartner's product hype cycle chart. Now, this is a chart that I saw at a presentation at University College London, Department of CASA, the Centre of Advanced Spatial Analysis, a UCL, absolutely innovative department, and they showed this slide 10 years ago, and it was the first time that I'd have heard of the Internet of Things. And at the moment, to look at the bottom of the x-axis here, you've got the technology trigger. This is all about the kind of, you know, the excitement about a new invention comes along, and then eventually you get this kind of peak of inflated expectations, and then you get this trough of disillusionment. And that's where probably you're waiting for the hardware to kind of catch up with your ideas. And then finally, you know, you reach to this kind of plateau of productivity. And this is why I thought, hang on, you know, 10 years later, we are actually here, we're in this world, and you know, it's like being a little boy in a sweet shop because you've got all these toys to play with. But I just noticed that we've got the Internet of Things, but not just that. I mean, we've also got, you know, NFC payment, contactless payment. We've got, you know, Netflix, internet TV. We've got augmented reality, which is another project that we're working at here with at Northgate. You know, where you're putting on the goggles and the goggles reveal this kind of hidden world, almost like a, you know, head-up display unit in an aircraft. You know, you can sort of, it reveals these hidden elements. Machine to machine communications, and that could be like REST APIs, where servers are communicating, you know, directly with each other. So you know, we've got this hype. 10 years ago, we got 3D printing, what other things, social TV, and again, we're in this world, and so we're in the world of the Internet of Things. And I suppose, you know, sort of think of a definition of the Internet of Things. I mean, I suppose broadly speaking, it's a kind of a network of like physical objects or things that are embedded with sensors and software and other technologies. I kind of guess for the purpose of connecting and exchanging data with devices over the internet. I'm sorry, a bit of a wordy definition, but the idea that, you know, that these devices can communicate with each other, and this is what we've taken on board. That this is part of our proof of concept. We wanted to take the Internet of Things and combine that with housing, and combine that with predictive analytics, and work out, well, what benefit or what actionable insights can we actually make from combining those elements. I mean, I'm sitting here, for example, with an iWatch, an Apple iWatch, and it's constantly, right, monitoring my health and with biofeedback, and it's constantly nagging me to stand up, run, jump, don't eat this, don't drink that beer, and I'm getting this immediate biofeedback from my iWatch. And you know, these devices are becoming more and more kind of popular, you know, Fitbit devices, etc. And the reason I mention that is because what we're interested in particularly is households that have we've installed or about to install sensors in properties to record temperature and monitor temperature and humidity, and that's and to provide a kind of an immediate feedback to the end user, both to the kind of tenant and to the organization, in the similar way that my nagging iWatch, you know, is giving me, you know, sort of like feedback and modifying my behavior. So again, it's sort of an interesting parallel there, sort of like, you know, sort of the iWatch and these sensors. And I think it's important that, you know, that installing these devices is, you know, these that are constantly monitoring temperature and humidity in our physical environment. I mean, remember that, you know, we probably spend, you know, about, you know, 70% of our time in our homes. And our homes are probably, you know, an extension of ourselves. And you know, a healthy home is a healthy individual. And probably, obviously, in COVID time, we're spending far much more time in our homes as well. So these sensors are almost like the Fitbit watches, constantly monitoring the environment. So okay, so that's part of the project we're looking at. Again, like I mentioned, you know, we're taking the Internet of Things, we're taking these you know, these devices, we're applying a bit of predictive analytics, and we're going to create a dashboard around that. And I'll show you that dashboard in just a minute. But I just really wanted to go through some of the benefits of why we're doing this. Again, bear in mind, this is just a proof of concept. And so the kind of broadly kind of thinking that, you know, what are the advantages here? We've got the tenant advantages, we've got savings from energy efficiency. Okay, that's, you know, taking data from energy devices and, you know, creating alerts if particular thresholds have exceeded, you know, in terms of kilowatt hours, etc. So, you know, we get an idea of cost benefit analysis. I think importantly, and I've got another slide, next slide goes into a bit more detail, is the health benefits. You know, there's, you know, if we're constantly monitoring you know, temperature and humidity, we're kind of adhering to the issues of like fuel poverty. I mean, fuel poverty, according to Public Health England, are defined as anything under, I believe, 18 degrees Celsius. So, you know, we can build a system that can create alerts to the tenant and the organisation that the person, you know, is at risk of fuel poverty. But, you know, with that fuel poverty, you know, you also got the you know, the health risks as well. And another one is reduced risk of hospital admissions. We've got chronic obstructive pulmonary disease, we've got asthma, all caused by kind of living in, you know, poor quality environments, low temperatures, high humidities. Again, you know, improve safety, obviously, carbon monoxide, smoke alarms. But with this proof of concept, what we're working on, we're just simply, you know, we're going to be focusing on temperature and humidity and interactions of that, and you know, the benefits. So property advantage, you know, obviously reducing carbon footprint and, you know, increased longevity of property and reduced maintenance. That particularly related to, you know, if we can predict if a device is going to fail by looking at its patterns of, historical patterns. We can see the patterns that will then lead to that failure of a device. So, you preempt it before it actually happens. And then you've got the organizational advantage, so the organization reduced the risk of, void properties, because unhealthy, unkept properties aren't going to be very appealing or desirable. So you want properties to be, sort of full of happy, healthy people, I guess. Increased savings, obviously preemptive maintenance, cost effectiveness. You've got logistic planning, efficiencies in property maintenance. You've got regulatory audit targets to be met as well. And probably that last issue there, you've got the legal kind of aspects to adhere to. You've got the Homes Fit for Human Habitation Act of 2018. Maybe actually relating. Maybe also insurance premiums that probably come into that. If you're monitoring your, the temperature and humidity of a property, I'm wondering if that might also impact on insurance. Anyway, probably a topic for discussion. Coming to the legal side, again, conscious of time, I've got quite a few slides to run through, but this Homes Fit for Human Habitation 2018 Act, I'm absolutely certain there are unscrupulous law firms out there willing to capitalise on this. So organisations need to be aware. So, that last point there, sort of list of possible issues that could render a property unfit include damp, mould, domestic hygiene, pest, refuse, etc. So yeah, okay, just like the Fitbit monitor I mentioned, or my nagging iWatch, having these devices and sending real-time information to kind of adhere to this. And then coming back to that health issue, this publication, this was in, front page news this time last year, the Health Inequality in England, the Marmot Review. And in this review, there's a chapter on poor quality housing harms health, and evidence shows that exposure to poor housing conditions, including damp, cold, mold and noise, strongly associated with poor health. I had the pleasure of interviewing this chap a couple of months back for another project we're working on homelessness. And also the degree in which we can predict homelessness. So I actually interviewed the author of this report, Professor Marmot, and throughout the interview, he was really hammering home the impact of poor quality housing on health outcomes. If you can see there at the figure, I'm pretty sure we can probably distribute this presentation afterwards, I do hope. But here we got housing, and you can see housing fairly, we look at the risk factor of housing is almost up there with smoking in terms of the burden to the NHS, £2.5 billion, and probably likely to be increasing. I would imagine. But yeah, again, another topic for probably a conference, I suspect there. So let's move on. What do we do to the data? So there's the justifications of what we're looking at, the Internet of Things, the predictive risk. Okay, what did we do with the data? Okay, so this wonderful infographic shows the kind of interaction of temperature and humidity. And what we were doing was trying to find the clusters. Let me talk a little bit around this visualization. So we've got relative humidity at the bottom, we've got temperature on the y-axis there. And as you can see, the properties that are in high humidity, fairly high, in temperature. If you're in this period of time for a duration, you're likely to have mold growth and also dust mites. I don't know much about dust mites, to be honest, but I'm more interested in these extreme bits here. So, and also, on the other end of the scale, we've got viruses. Viruses, we've got, COVID-19, that goes up, the R rate of COVID-19 goes up, exponentially at low temperatures, apparently. So, we've got fuel poverty there, which I mentioned, PHE, that kind of threshold of 18 degrees Celsius. And so this is where, if your property is in this zone, or on a continuum, as in it hasn't just randomly just gone down there for a day, it's in there for a while, you're likely to have this kind of viruses and health risks, etc. And what we did with the data, again, I don't want to go into too much granular level detail. We kind of took the data, which is model data. Bear in mind, this is model data from a third-party company who have modeled the data, provided us the data. We're getting the data via REST APIs. That's that server-to-server communication. And we're taking that data, we're going through a process of derivations. We kind of work out, the average weekly temperature and humidity. We try and spot outliers. But then we applied something called a k-means cluster, which is a kind of a predictive risk or predictive kind of algorithm. It tells you which of these groups you're likely to fall into, drawn on the data and your historical data. So looking at the patterns of data, the property could fall into zone 4. We call these habitable zones. The fuel poverty zone, the acceptable zone, which is probably about 90% of the property is going to fill in this kind of probably Goldilocks zone. We call it the Goldilocks zone. Not too hot, not too cold, and then maybe 5 or 10% of the properties will fit into this kind of mold growth zone there. So that's what we did. We used like k-means cluster, and very broadly, the data did kind of, we threw the data into the algorithm. The algorithm turned around and said, well, actually, looking at the patterns of data, looks like you've got 3 groups. And then we looked at the academic research and thought, hang on a minute, these 3 groups kind of align with these 3 clusters.
Steve, sorry to cut you off mid-flow there. I think we've only got a couple of minutes left.
Yeah.
We're almost a half past, so if we can try and cut it to a couple of minutes, that's okay.
Yeah, hey, no worries. We're coming into the last 2 slides here now. Okay, so what we took with the data, we took the data and put it into a kind of reporting dashboard. So we could geocode the properties, we could put that in a map, we can identify the property. So this one here has got very high humidity, yearly average humidity. We've got the kind of a feed here, timeline feed, where we can look at the daily temperature, the daily humidity. These blobs here are identifying anomalies in the data. So if I click on one of those, it will say, well, actually, this falls outside the expected temperature. And more importantly, we've got this one at the bottom there, which is like the average daily above 80%. So that's like, that's really important. But what's really important is that we've got this kind of we've got that cluster here. So with that cluster in the previous chart, we said that particular property could fall into the habitable zone called potential mold growth. And we've got another algorithm output, which is like we're saying that this person is also likely to give up paying their rent based on another risk algorithm. So that's just, we've then also added these kind of 360-degree kind of data, external data, as in kind of like, the deprivation score and, what are the other property, is it in a high deprivation zone? For example. So that's, we kind of create this dashboard to feed all the data in. So the next $1 million question is like, well, okay, what's driving that habitable zone? What are the influencing factors driving that habitable zone cluster? And that's the next screenshot. Hopefully this is one of the last ones, I do promise. So we've got this kind of what influences the cluster here. We've got potential mold growth. So we've got, remember those 3 clusters, we had fuel poverty, the acceptable zone, and then we can select from the cluster, what are the issues? What's the likelihood of habitable zone being in potential mold growth? Well, we've got these 3 factors. Remember, this is model data. This is the issue, which is like driving that mold growth, i.e. the ones within in this particular zone, these particular properties don't have any glazing, their EPC rating is very poor, it's G, for example. And you can see what are drivers, and coming back to the earlier slide, so coming back to sort of Jon Snow's coroner, these are almost like the water pump handles, in a very crude analogy, obviously, but these are the kind of drivers, which is pushing the property into potential mold growth. So okay, so I think that's again, sorry, conscious of time, that's about. I've got a couple of slides here just to go into a bit more detail. I'll just quickly run through what we've done.
I don't think we've got much time for those, Steve. I think
okay,
we'll probably, if we can circulate those afterwards, that'd be great. I think the appendixes, I think we'll crack on with the discussion.
Brilliant.
If that's okay.
Yeah, no, that's absolutely fine. Apologies, I might have run over a little bit there, but obviously a lot to discuss there. Probably enough detail for a conference.
I think.
But yeah, thank you very much. Cheers.
Probably enough as well to get us started with the discussion. That was really good. Thanks very much for that, Steve. There's already people, starting to comment with some questions. So, I mean, I guess I'll just stop the recording just now.